Namaskar and welcome to CEC Gurukul Lectures. I am Dr. Kumar Shantanu, Associate Professor of Botany from Deshbandhu College, University of Delhi. In this new series of lectures on analytical techniques used in plant sciences, we have started our journey with an understanding of one of the very basic analytical tool, that is microscope. In our previous lecture, we have talked about two fundamental types of microscopes, that is light microscope and electron microscopes. We have also understood the various comparison between light microscope and electron microscopes, the limitations of light microscope and electron microscopes, the advantages of light microscope and disadvantages of light microscopes. We have also seen the various fundamental elements which are used in any microscopy. Today, in this lecture, we are going to continue our discussion on the principles of microscopy. A light microscope uses glass lenses to direct photons, whereas an electron microscope uses electromagnets as lenses to direct electrons. However, both kinds of microscopes have two fundamental properties in common. One is focal length, the other one is angular aperture. Let us try and understand how and in which manner these two fundamental properties affect the magnification of the image and also the resolution of an image. So let us try to understand the magnification with the help of a diagram, a schematic diagram. So in this schematic diagram, you could see that the magnification of any object is nothing but it is a ratio of the height of the image created upon the height or the length of the original object. Now, the relationship between the height or the length of image created, which is mentioned here as V, and the length of the object, which is mentioned here as U, with respect to the focus of a lens or the focal length of the lens, is like this, that 1 upon V minus 1 upon U is equal to 1 upon F. So the focal length is inversely proportional to, or it is inversely related to the magnification capacity of any lens, and this is true for both the types of lenses, that is convex lens and concave lenses. The focal length is determined by the index of the refraction of the lens itself, the medium in which it is immersed, and the geometry of the lenses. The lenses which are made up of any kind of material, so any material which is not vacuum or which is not air, will allow the movement of light in a different manner, and this will be determined by its refractive index. The magnifying strength of a lens, which is also measured in diopters, is the inverse of the focal length, which is measured in meters. The angular aperture, on the other hand, refers to a measure of how much of the illumination that leaves the specimen actually passes through the lens, and thus it determines the sharpness of the interference pattern, and therefore the ability of the lens to convey information about the specimen. The angular aperture is about 70 degree in the best of the light microscopes. So it is the resolution and not the magnification which is more reliable estimate of the utility of a microscope. There are three factors which influence a microscope's resolution. The first one happens to be the wavelength of light, which is used to illuminate the specimen. The second factor is the angular aperture, and the third factor happens to be the refractive index of the medium surrounding the specimen. We can understand the concept of numerical aperture for objective and condensers with the help of these diagrams. So this is the path through which an incident light is coming, and it passes through a specimen plane. Because of the physical nature of the specimen, the pathway of the light is hindered and it takes a different course. The objective this different course is called as the objective aperture angle, sometimes also denoted as alpha. And with this angle alpha, the light reaches to the objective lens. And then because of the property of the lens, it further gets corrected in a further movement. So here the objective aperture angle happens to be alpha. On the other hand, if we talk about a condenser, the condenser beams all the light towards the specimen. So this movement of parallel beam towards the specimen is the condenser aperture angle, which is denoted as alpha, and the objective aperture angle is again alpha. So the total aperture angle here happens to be 2 alpha. The effect of these variables on resolution is described quantitatively through Abbe's equation, and this Abbe equation says that resolution is equal to 0.61 lambda upon n sin alpha. In this entire equation, R is representing resolution, lambda is representing wavelength of light which is being used to illuminate the specimen. N is the refractive index of the medium between the specimen and objective lens of the microscope, and alpha is the angular aperture. Since the refractive index of the medium and angular aperture remains same, so sometimes it is also represented as Na. Now let us talk about the light microscopy. The most basic mode of, or the most basic model of light microscope is called as bright field or bright background, which can be achieved with the minimum optical elements. Here is a diagram which represents a bright field microscope. In this diagram, we can see that the light source happens to be a visible light, or the illumination source happens to be the visible light, and it gets converged with the help of condenser lens on a slide, and this slide or the specimen refracts and it changes the course of light, and these lights after interference and diffraction passes through the objective lens, and these objective lens ultimately creates an image on the eye or on the detector sensor. So there are different types of light microscopes, but all light microscopes include a system of 3 glass lenses. The condenser lens that focuses light from the source onto the specimen. The objective lenses which magnify the specimen to different degrees, and the third set of lens happens to be the eyepiece lenses, which further magnify the image. So we can see with this diagram that in a bright field microscope there are three sets of lenses. The first set of lens, which is closest to the light source, happens to be the condenser lens. The condenser lens focuses the parallel illuminating visible light beam towards the specimen which is kept on the specimen stage. Now, because of the physical nature of the specimen, the light is further getting scattered through a process called as interference and diffraction, and these light rays then passes through a second set of lens called as objective lens. These objective lens converge these light beam, and then it passes through a third set of lens called as eyepiece. The eyepiece then finally forms an image of the specimen which is observed by the observer's eye, or it can be recorded with a digital camera as well. The light microscopes happens to be inexpensive and simple to align and use. The contrast in images can be obtained from such microscopes, which is usually produced by the color of the object itself or by exploiting some other properties that affects the amount of light that can pass through. In the light microscopy, we could use some kind of stains also, which goes and binds to a specific area of the cellular structures, and it imparts a contrast which can be perceived by the visible eye. So this kind of microscope is therefore used to collect images from pigmented tissues or histological sections, or from tissue culture cells that have been stained with dyes. Major components of all modern light microscopes, it includes a condenser lens, the objective set of lenses, and the eyepiece lenses. And each of these components in turn are made up of a combination of lenses. So let us talk about the main components of a compound light microscope. A compound light microscope has 5 major components. The first happens to be the light source. It is the source which illuminates the specimen. It can come from below the specimen or it can come above the specimen. The second component happens to be the stand, and the third is the specimen stage, fourth objective lens, and the fifth is eyepiece. So out of these 5 components, the 3 happens to be the physical structures, the 2 happens to be the set of lenses. Let us try and understand these 5 different components one by one. So what is a light source? A light source is a proper illumination of the specimen, and it is important for achieving a high quality images and photomicrographs, and this is achieved by using any kind of light source. A good quality of light source typically includes mercury lamps, xenon lamps, laser or light emitting diodes, that is LEDs. In basic laboratories, sometimes we use daylight also as our source of illumination. In such cases, we provide a condenser, a concave mirror which gathers the room the available ambient sunlight, and it focuses these ambient sunlight towards the condenser, and then the condenser further beams out these light onto the specimen. Let us try and understand these components of a compound microscope with the help of a picture or a schematic diagram. So here in this schematic diagram you can see that the source of light is lying at the bottom of the specimen stage. So the light source could be a lamp which is a xenon, which can be a xenon lamp, it could be a LED lamp, and but whatever the source of light is, or whatever the component of this illuminator is, the wavelength always happens to be in the visible range. Now light from the light source passes into the condenser lens. The condenser lens is mounted beneath the microscopic stage in an upright microscope, whereas in case of an inverted microscope, the condenser lens is mounted above the stage. So the condenser lens, when the light passes into the condenser lens in a bracket that can be raised and lowered for focusing. So it is very important to have a good positioning of condenser lens to have a proper illumination of the specimen. The specimen is illuminated with parallel beams of light through the condenser focused light from the light source. The light then passes through the specimen and it is reflected back from the specimen. So when the light passes through the specimen, it is called as transmitted light, and when it is reflected back from the specimen, it is called as the reflected light. So the light that passes through the specimen, or which is reflected back from the specimen, is focused by the objective lens into the eyepiece lens. The image is either directly viewed by the eye in the eyepiece, or it is often projected onto a detector such as photographic film, or more likely a digital camera. Now the second component of a light microscope is stand. This part of microscope holds all the components firmly into their position. There are two basic types of microscope stand: an upright one or an inverted one. The light source is below the condenser lens in the upright microscope, whereas the objectives are above the specimen stage, and this is the most commonly used format for viewing specimens. Whereas the light source is below the condenser, whereas the light source is above the condenser lens in an inverted microscope, and the objectives are below the specimen stage in some of the light microscope. Here you can see the basic structure of a light microscope, and a very firm and a curved structure which holds almost every component of a microscope. This is called as the arm or the carrying handle. Now the carrying handle holds the objective lens and the ocular lens above the specimen, and it also holds the light source and the condenser lens below the specimen on the lower side. And this stand or handle or arm is also used to give a proper firm position to all different components. This is the place again where the coarse and fine focus adjustment screws are also adjusted or fitted with. As we have already talked, in an inverted microscope, the light source and the condenser lens are above the specimen stage and the objective lenses are always beneath it. The condenser and light source can often be swung out of the light path, and this also allows additional room for manipulating the specimen directly on the stage. Now the third component happens to be the specimen stage. It enables the specimen to be moved and positioned in fine and smooth increments, both horizontally and transversely. And it can move in x-axis and y-axis directions for locating a region of interest. So the specimen stage is moved vertically in the z-axis direction also for focusing the specimen, unlike in inverted microscope where the objectives are moved and the stage is fixed. So specimen stage is one platform which is movable in upright microscopes. This movement can be in all the three axes, that is, it can move horizontally, it can move laterally, and it can also move in a vertical direction. Here you can see the diagram of a microscope with the help of this picture, where mechanical stage or specimen stage is the place where all the specimens will be put together, and this can move in all the three dimensions, that is, it can move horizontally, it can move in a lateral direction, and it can also move in a vertical direction. And because of this movement, rest all the components are always fixed, and the specimen can be adjusted so that it lies in the path of light beam. There are usually fine and coarse focusing controls for high and low magnification viewing respectively. For high magnification, we use the fine focus, whereas for low magnification, we use coarse focusing controls. The fine focus control can be moved in increments of up to 1 micrometer in the best research microscopes. The specimen stage can either be moved by a hand or a stepper motor attached to the fine focus control of the microscope, controlled by a computer. The last component happens to be the objective lens. This component is responsible for producing the magnified image and can be the most expensive component of the microscope. Objectives are available in many different varieties and with much information inscribed on each one. This information can include manufacturer information, magnifications such as 4x, 10x, 20x, 40x, 60 and 100x. Immersion requirements such as air, water or oil requirements, cover slip thickness and more specialized optical properties of the lenses. So here in the diagram you can see that objective lens, they are the most expensive ones, and they are the set of lenses which receive the transmitted light. The objective lenses can either be dry lenses, that is glass air cover slips, or they can be immersion lenses such as glass oil or water cover slips. Generally, most objectives below 40x are air objectives, and those of 40x and above are immersion based objectives. An objective designed to operate in oil will be labeled as oil or oil. Other immersion media include glycerol and water, and the lenses will be marked accordingly. There is even a mark for numerical aperture on the lens. A number usually between 0.04 and 1.4 is mentioned. Lenses with a low numerical aperture collect less light than those with a higher numerical aperture. High power objectives with a higher numerical aperture have a better resolution than a lower power lenses. The objective lens is most prone to be damaged by mishandling, although many lenses are coated by some kind of protective coatings. And the last component happens to be the eyepiece. It works in combination with the objective lens to further magnify the image and allows it to be detected by eye, or usually to project the image into a digital camera for recording purposes. So eyepieces usually magnify by 10x, since an eyepiece of higher magnification merely enlarges the image without any improvement in resolution. So there is an upper limit to the useful magnification of the collection of lenses in a microscope. So here in the picture you can see the eyepiece, which usually is of 10x magnification. So the light microscope which we have discussed till now, we have seen that these microscopes have 5 different components, and in our next lecture we will try to understand the basic concepts of a stereo microscope and how the contrast in phase of the light can also enhance the quality of image created, and we will try to talk about the phase contrast microscopes, and then we shall move on to different types of electron microscopy. Thank you so much for your patient listening.